This talk will be about a scientific application of the ECCO ocean reanalysis, focusing on its modeling system, especially its adjoint. My co-authors are O. Wang and Ian Fenty, who's in the audience. We'll begin with a brief overview of ECCO, the Global Ocean Analysis of the Consortium for Estimating the Circulation and Climate of the Ocean. I'll then introduce EMU, short for ECCO Modeling Utilities, which is a new suite of computational tools that allow users to run the ECCO model and its components, including the model's adjoint, without requiring modeling expertise. Finally, I'll briefly describe how we apply EMU to a recent study of climate change in the Arctic Ocean, uncovering a shift in climate that is not well resolved in traditional reanalyses. ECCO is a NASA Global Ocean reanalysis that incorporates nearly all available satellite in situ observations. It's what is known as a smooth estimate, which adjusts the model's independent controls, such as model's initial condition, forcing, and model parameters. It's a fixed interval smoother, where the interval is the entire analysis period of 30-odd years, solved by the adjoint method, also known as 4D VAR. This approach ensures that the corrections to the model state adhere to model's physics, resulting in an estimate that is consistent with both observations and physical principles, such as budget closure. This is illustrated by this blue curve, a continuous blue curve that connects ECCO's state estimates, in contrast to discrepancies that exist in filtered estimates in red. However, if one just focuses on the state, as illustrated by these symbols, the difference between the two types of estimate may not be immediately obvious. The fact of the matter is, the physics that the smooth estimate is consistent with is embodied in the model itself, represented by this blue curve. The model not only produces these estimates, but also evaluates the physical processes underlying its evolution, such as mixing, transport, wave dynamics, and dynamic balances that shape the ocean state and governs its evolution over time. This motivates us to analyze the model to gain insight into these processes, which is often not apparent from the state alone. To this end, we've developed EMU, the ECCO modeling utilities. EMU is a set of menu-driven tools for analyzing the ECCO model. The key words here are menu-driven and model. Being menu-driven, the tool requires no modeling expertise, similar to Apple computers, which have always been easy to use without a manual. EMU separates the technical task of running models from their scientific applications, allowing users to focus on the science. EMU analyzes the model itself, not just its output, enabling tasks such as computing adjoint gradients, evaluating budgets, running perturbation experiments, and computing additional variables beyond the standard output. Importantly, EMU is we've also containerized EMU for portability, allowing the tools to be run on anything from personal computers to high-performance servers to the cloud without compilation. The tools are available on GitHub at this address at the bottom. Using EMU is straightforward. After typing EMU at the shell, the interface will guide you through selecting tools from a menu. Here we choose option 3 for the Adjoint tool. EMU will then ask you for the details of the quantity of interest, and then it will proceed to compute its adjoint gradient automatically. EMU was recently featured in an ECCO Hack Week event where over 20 students learned how to use ECCO's products and tools. In just a few days, without prior modeling experience, the students were computing adjoint gradients and using them to study such things as transport and heat content changes, which demonstrates the ease of use of the tools. The Hack Week website provides tutorials in Jupyter Notebooks available at the highlighted link. Now, we'd like to take a closer look at a practical application of these tools. This study concerns climate change in the Arctic Ocean, highlighted by the green arrows in these time series going clockwise of sea level in the top left, freshwater content, and sea ice area, averaged over the Beaufort Sea. This Beaufort Sea region, outlined in black on the map, has the largest sea level rise across the globe, reaching 20 millimeters a year, which is an order of magnitude greater than the global average. ECCO's estimate in black closely matches observations in color, showing a sharp increase in sea level and freshwater content, and a decline of sea ice area. Importantly, ocean bottom pressure remains stable, meaning that this sea level rise is steric. In fact, it's entirely halosteric, reflecting the increase of freshwater content. To understand the cause of these changes, we decompose the Beaufort Sea mean sea level, J on the left-hand side, in terms of its drivers, represented by the ocean's forcing, phi, on the right-hand side, using gradients, adjoint gradients, computed by EMU as coefficients. This approach, called adjoint gradient decomposition, approximates the first-order Taylor expansion and provides and quantifies what forcings contribute to this variation. Unlike correlation or other empirical measures, this equation describes a causal relationship between forcing and its effect. While adjoints are typically associated with data assimilation, here we're using the adjoint for an entirely different purpose. This expansion consists of 3 separate sums over different types of forcing indicated by I, such as wind forcing and heat flux, the forcing's location, R, and the time lag, delta T, between the forcing and the quantity of interest, J. This equation allows us to identify what type of forcing, at what location, and when it causes the variation on the left-hand side. The bottom figure on the left shows the accuracy of this approach, comparing the left-hand side of the equation in black and the sum of the terms on the right-hand side in green. The agreement between black and green reflects the physical consistency of the ECCO estimate and demonstrates the fidelity of this expansion. The right figure breaks down the first summation to identify the drivers, the dominant drivers of this variation. The main contributor is wind in orange and freshwater flux from sea ice melt in blue. Since sea ice is fresher than seawater, its melt occupies a larger volume than what it was displacing, raising sea level despite Archimedes' principle. These plots show where this forcing occurs, calculated as explained variance mapped according to this equation using this expansion. The left figure illustrates the wind's contribution, and the right figure is sea ice melt. The wind's contribution takes the shape of a donut around Beaufort Sea with a hole in the middle. This reflects increasing Ekman convergence of fresh surface water from the surrounding regions. We see the largest contributions at the southern end, where the change in wind is the largest. In contrast, the sea ice melt's contribution takes the shape of a pancake, with the largest freshwater input occurring over the Beaufort Sea. The patterns are different, but this also reflects an increase in Ekman convergence of sea ice being converged into this region and melting it here instead of elsewhere. This is what the wind looks like. The plot shows the strength of the wind measured as Ekman pumping integrated over the region. ECCO's estimate in blue, the magnitude increases threefold from before to after 2007, which is far larger than the estimate by ERA interims analysis. While this discrepancy is notable, other evidence suggests that ECCO's estimate may indeed be sensible. For example, satellite data shows a threefold increase in the magnitude of the surface current and a significant acceleration of sea ice drift shown in the left panel.
Sorry to interrupt. We're into your question time now, so if you could wrap up in the next minute.
Okay.
Thank you.
There's a sea ice acceleration and a dramatic decrease in ice loss over Greenland, indicating that there's a major shift in climate around this time. Last slide. In summary, EMU enables analysis of the ECCO model, including its adjoint, with minimal effort. These tools allow analysis that is difficult to conduct with the state output by itself, and we advocate for wider availability of similar tools. Applying this tool to the Arctic shows that the rapid sea level rise observed in the Beaufort Sea is a result of a major shift in Arctic wind around 2007. However, the nature of this change over the Arctic remains unclear, and we welcome any thoughts and input. Thank you.